So yesterday we were talking about coming up with a framework for our algorithm analysis. Then we talked about the mathematical model, which is a RAM model, random access memory model, which has processor and memory. And given a problem, you are going to develop an algorithm, which is a set of instructions to solve the problem you are going to write. Then you should know that the CPU, central processing unit, in our RAM model is going to execute these instructions. And before giving an algorithm, writing an algorithm, you should know the problem specification in terms of valid inputs which can be given to our algorithm, and what is the expected output or outputs from this algorithm. Then our RAM model has a CPU which takes instructions in a sequential manner. That's the model we are looking at, and it executes the instructions, and we should know how much time each instruction is going to take. And in detail we have seen, if given an instruction, what does how much time it's going to take, how many steps it's going to take. That we have seen with examples for mathematical, arithmetic and logical operators, or it could be a looping structure, or it could be an arrays. And we have seen how much time it's going to take. So you will have a knowledge when you are writing an algorithm, you will know what kind of instructions your RAM model is going to take. So given a problem can be of different type. It could be GCD, it could be finding whether a cancerous cell is benign or malignant, or it could be finding a shortest path given a map and 2 cities. If I say you find a shortest path between Bangalore and Mysore, and there are a lot of roads connecting to these 2 cities, and if you are given a map with 1,000 cities and the roads going in between them, then you need to represent the problem. This is a problem statement if it is given to you, then you are going to model it as a graph, and graph will have node, and the roads between these cities are represented as a edge. Then you are going to give input as a adjacency matrix or adjacency list, as we have discussed earlier. And if you give 2 city name and a map, on the map you should plot the shortest path, like you see it in the Google Maps when you are driving and trying to see shortest path in terms of amount of time it's going to take. Also could be the weight which you are looking at. So the for the GCD problem, it is the input which matters. It's a numerical input. That input may not be relevant to the shortest path problem, because there you are using map and the city names from which source to destination you want to travel. That could be the input, and output is the path, the shortest path plotted on the map. Similarly, when you are finding whether the cell is cancerous or not, it is malignant or benign, the input could be a MRI image, which will take photographs of soft tissues, and you need to come up with a binary classification. After writing an algorithm, you should say whether it is benign or malignant cancerous cell. So once you know the specification of the problem, once you know the model, what kind of data structures you are going to use, and all it is all information, right? We are in this particular topic, we are trying to come up with a formal framework for algorithm analysis, because we are developing many algorithms to solve many problems, and we would like to compare them. We would like to evaluate each algorithm's efficiency in terms of time and space. So time is called time efficiency or time complexity. For space, it is called space efficiency or space complexity. So that was the discussion. Then we talked about space complexity. And we talked about a fixed part which is required by your algorithm, then the variable part. And I have given you the 3 examples in which we have also seen the size of the variable part, size of the memory which your algorithm require depends on the characteristics of instance, right? So next we talked about time complexity, because to execute the instruction, your processor is going to take certain time and each instruction takes certain time, and we wanted to evaluate the performance evaluation we wanted to do. And there are 2 kinds of time complexity or performance analysis you can do. One is empirical analysis, which is called a posterior analysis or profiling, in which once the problem statement is given to you, you take the problem statement, you develop an algorithm for our RAM model, then you use that algorithm mentally, you use that algorithm, then you will convert that into a program. So you may select some programming language. With the rules and regulations of that particular language, you write a program. Once you write a program, you are going to run this program on a computer to check how much time it is going to take. So this is also called as profiling. Profiling is the process of executing a correct program on data sets and measuring the time and space it takes to compute the results. So this is required if once the program is implemented, you should give all sorts of input, the test cases which needs to be given, and you need to see you are getting a correct results or not. So you need to, profiling is also necessary in the study of performance of an algorithm to check the quality of results computed. So that's the one kind of analysis which you can do. In fact, you are in this course, you are going to do an assignment at the end of each course, wherein you implement some algorithms in the assignment which we are going to give you, and you are going to plot the results. So you give different size inputs, and for each input or instance size, you are going to see how much time it's going to take. Every time you are going to increase the size of the input, and you are trying to see plot the graph, right? See the input on the x-axis and that amount of time it takes on the y-axis, and you are going to see plot that results which you have got, and you are trying to see how much time it is going to take, and you are going to by this you are going to do the analysis of the algorithm practically, right? So this is called empirical analysis. We will see if you are doing empirical analysis before deciding the efficiency of algorithm, and what are all the drawbacks of this. We are going to do that in our time complexity. Then there is one more type of estimate which we can do is theoretical analysis. What does it mean? We are not going to convert our algorithm into program at all. So you have written, you took a problem statement, you saw the specification of the problem statement, and you are going to come up with an algorithm for our RAM model without implementing, without using any programming language, using those instructions which you have written in an algorithm. You are going to do the analysis, and that is what we are going to do in the while coming up with a formal framework. And we are going to see how we can do without running our program converted without a running program, how we are going to evaluate the algorithm performance in terms of time and space. Mostly it is with time. So that's what we are going to do. That's called theoretical analysis, and it is also called as a priori estimate. So we are talking about time complexity, the amount of time your program is going to take. It depends on two things: the time taken to compile the program and to run the program. Probably not, because it does not depend on the input instance characteristics. It takes compile time is a constant time it's going to take when you compile the program. It does not depend on the size of the input instance. You agree, you all agree, right? So during compilation, we are not going to give input. So it does not depend on the input instance characteristics. And also, once you compile, you can run this program many times without compilation. You compile, you got an executable and you use it with the different data sets. So once compiled, it will run several times without compilation. So we don't have to worry much about the compile time. That's what I'm trying to say. Our concern is the runtime of a program. So what is runtime? So when you run the program, it's going to take certain time, and you all agree with me that this runtime depends on the instance characteristics. Yes or no? Are you able to hear me? Am I audible?
Yes, sir.
Are you able to look at the PPTs which I'm showing?
Yes, sir, it's visible.
I'm just confirming because I need to check in between. Okay. So does it make sense? Should we, when we are finding the time complexity, should we really worry about compile time or not? It's not, right, because it does not depend upon the input characteristics, and once you compile, you can use, you can run many times. So, but runtime, does it depends on the instance characteristics?
Yes, sir.
Why?
It depends on the size of the input.
Because the looping or the most basic operation which you do will depend on your n, right?
Yes, sir.
Okay. So then it is reasonable to find time complexity. To find time complexity, it is reasonable to estimate only the runtime. So we all agree that we will estimate only runtime while finding the time complexity of a algorithm. So that we will agree upon, and we will proceed. So this gives you, the next slides which I'm going to show talks about how we are going to come up with a framework. So the framework says measuring an input size is important because the amount of time taken depends on the input size. Then we need to measure the running time. It could be seconds, milliseconds to run the program. We will see whether we need to measure it in seconds and milliseconds or something else. So that's what important in measuring in the running time, and we also will be concerned about units of measurement of a running time, and we will see whether it is required or not. The discussion will happen whether we should represent a running time using some units like seconds and milliseconds or not. Then we will see that our algorithm efficiency is we will be considering order of growth, which depends on the size of the input. As size of the input increases, the amount of time also taken increases. For smaller input, the time taken is less. When you increase the input, it's going to take, time which is greater than the time which is taken for the smaller inputs. Then we also, our framework also, in the framework we also discussed that it's not only the size of the input which matters when you are calculating the efficiency of an algorithm. It also depends on the type of input which you are going to give. So that's the gist of the framework which we are going to come up with. So the formal frameworks talk about measuring an input size, measuring a running time. We always specify the efficiency of algorithm using orders of growth, and we'll see what is this orders of growth does mean. And we will also see that finally we will also see that the efficiency of an algorithm does not only depend upon the size of the instance, it also depends upon the kind of input which you are giving, right? It also depends upon the specification, right? On the input side, but also on the specifics of the particular input. You are once given an input, what kind of input we are giving, the specifics of input also is checked to come up with three types of efficiencies: worst case efficiency, best case efficiency. This is worst case there, not base. Worst case efficiency, best case, and average case efficiency. So the first one is measuring the input size. Let us start with the first point in our framework. As all of you know, almost all algorithms run longer on the larger inputs. For example, if it takes longer to sort larger array, multiply larger matrices, and so on. So it becomes logical. Therefore, it is logical for us to investigate an algorithm efficiency as a function of some parameter n indicating the algorithm's input size. So we will be defining our efficiency in terms of input size, right? So it's not difficult to find the input size given a problem to you. For example, if you are given a problem to sort elements in ascending or descending order, what could be the size of the problem? It's n, right? What is the input size of the problem for sorting? It's the n number which you are going to sort. Because when you compare, you will be comparing these n numbers. So each comparison in our RAM model is going to take certain time. So the input size depends on the problem. For sorting problem, it is n. What is the size of adding two n by n matrices? It's n as well here, right? So the dimensions of a matrix, if it is a n cross n matrix, then it is n as well for the adding two matrices. So measuring an input size becomes very important for investigating an algorithm efficiency. That's the first point, or when we are coming up with the framework for algorithm efficiency, the first step is to check the size of the input, right? Next one is measuring the running time. So we need to measure the running time of a program implementing an algorithm. Once you have developed an algorithm, you convert into program and find the running time. So should we measure the running time using the standard unit of time measurement like second, millisecond, which depends on the machine where you are running? So obviously no, because there are a lot of factors it depends on, right? So the amount of time which our algorithm or program is going to take depends on the speed of the particular computer, and also it depends upon the quality of program implementing the algorithm. It depends on the programmer, how does he implements our algorithm. If I develop an algorithm and give it to some programmer and he chooses the program and he also program the algorithm, taking each instruction, then it also depends on the quality of program he or she writes, right? So it depends on the quality of the program the programmer is implementing, and also it depends upon the quality of the compiler generating the machine code. What kind, you may use different kinds of compilers to compile this, and the compiler will generate the machine code. Is this an efficient one or not? That depends on quality of the compiler which generates the machine code. And it is very difficult in clocking the actual running time of a program. Why? Because in a multi-user system, there may be many tasks which are running in your system, and it has to be same every time when you run this program or run the different algorithms for solving the same problem. So it is very difficult for you to clocking the actual running time of the program, because in multi-user system there are many programs running, and it's a single processor, and all these programs are sharing this processor. So when you wanted to clock and find the exact time, it is certainly difficult for you. So the metric which we try to use by running our code on the machine after converting our algorithm into code, it depends on, or it is affected by lot of these external factors, right? And also, if you are comparing a set of algorithms, like if you are given a problem of sorting a numbers, and using different algorithm techniques, you develop three algorithms for solving the same problem of sorting. Then before you could select one of this algorithm for final implementation, you need to implement all these algorithms. It's going to take time to develop all the algorithms. And we are only interested in algorithm efficiency. So we are going with the theoretical analysis, and we'll see the analysis which we are going to do theoretically, and conclusion which we are making also works for real-time computers. That's we are going to prove. It may not be exact time which we are going to find. It's an approximate time which we are going to find and make our assumptions, and we are going to come up with conclusions. But we will see that our conclusions which we make on our RAM model, and not even implementing the program, we are trying to find out the efficiency of an algorithm. You will see at the end of this topic that our conclusion will really apply to the real computers. So what we are trying to do? We are trying to see notion of unit time. It is not second or millisecond. Each operation takes unit time. It consumes unit time for each operation for our theoretical analysis. So we come up with a notion of the amount of time consumed by each operation in your algorithm. What we are trying to do? So we are trying to count the number of times each of the algorithm's instructions are executed, right? So if there is 100 lines of algorithm which we have written, then each instruction we will take, we will count as I have shown you that when I say A of I is equal to B of I plus C of I, it takes 4 steps. So each step count we are going to take, and we are counting the number of times each of the algorithm's instructions are executed. Then we will say how much time it's going to take. And in a couple of lectures which I'm going to give you, you will also see it's very difficult and cumbersome process to find out the number of steps for each of the instructions in the algorithm, and you also see it is unnecessary. Why it is unnecessary? I'll show you. So it is difficult and it also becomes unnecessary, and when we come up with a formal framework, you will agree with me that it is unnecessary. So this is how we are going to measure in the running time. Is that clear? Any doubts, any clarifications here? Anything you would like to ask? Is the point clear? Why we are not going for seconds or milliseconds, or running our program onto the machine and trying to find out the time complexity?
Yes, sir.
Will all of you agree that it depends on it is affected by the external factors mentioned above, the 4 points which are given here? Yes or no?
Yes, sir.
Okay. So what is the way out for us? Is notion of a unit time. Like we say that each of the following operation consumes unit time, like arithmetic operations, plus, minus, star, divide and modulus. Each of these steps takes 1 unit. If you compare elements, right? So these comparison operators also takes unit time per operation. Logical operations like NOT, AND, OR, XOR also takes an unit time. And if you assign something, like if you say C is equal to A plus B, first A is fetched, B is fetched, it is added, 1 unit of time it is going to take for addition. Then you are going to assign it to C, then this assignment operator also we consider as 1 unit time which it's going to take. So let us see how much time it's going to take for the algorithm which we have written in our earlier class. For if you don't have a multiplication operator, then you have to do repeated addition, and that algorithm was written, and we will do the analysis for that particular algorithm. Okay. So what was the algorithm? We will initialize p is equal to 0. Then we will run our loop from 1 to n, because m and n, you are going to multiply m star n. So if you have written an algorithm for that, the algorithm looks like this, right? So here you can see initializing p is equal to 0. Then we run for loop from 1 to n times. Every time we add the number repeatedly to multiply m into n. I hope this algorithm is clear to all of you. Yes or no?
Yes, sir.
Can you look at the table and do the analysis? So what we have said in the previous slide, arithmetic operators, logical operators, assignment operator is going to take how much time?
Unit time.
So unit time. The first step, P is assigned with 0. The operation which is done here is assignment, isn't it? How much time it is going to take?
Unit time.
Unit time 1. How many times we are going to assign 0 to P in our algorithm?
Once.
So once only. So number of times we are assigning 0 to P when multiplying m star n is only 1 time. So P is equal to 0. This one is an assignment operator. It takes unit time. The number of times it is, it is executed is only 1 time. Next is our for loop. How many steps it's going to take in terms of operations? So your assignment 1, right? Then you are going to increment, right? I is equal to I plus 1. So you are going to increment every time you are going to increment, right? So once you increment, for increment, that is I plus 1 takes 1 operation, and assigning this updated value to I is 1 operation, and you will check the condition whether I is greater than n or not. That is comparison operator. So increment, assigning the value to I is 1 operation, increment is the other operation, and comparison. So totally when you run a for loop for n time, for each time you are going to do 3 operations. So how many times we are going to do these operations? Can you tell me? All of you are there?
Yes, sir.
Yes, sir.
So how many times you are going to do this?
We check the condition n plus 1 times, but all the other operations are just.
So why n plus 1 times?
So the
Interesting,
last
right?
time,
So,
the last condition when it becomes false, that's the extra one.
N
yeah,
plus.
so correct. You're correct. So it's n plus 1 because the last operations which we are trying to do, are you able to see the table?
Yes,
Yes,
sir.
sir.
So the for loop, the statement inside the for loop or the for loop itself runs for each time when you execute the for loop, it takes 3 operations: assignment, increment, and comparison. It is number of times you are going to do is n plus 1. Then there is a statement inside the loop, that is p is equal to p plus m. How many operations are performed here? 2. One is assignment, one is addition. So 2. So each time you do this, execute this statement in your algorithm mentally. So how much time it's going to take? It's going to take 2 units of time. How many times we are going to do? N times only. Because when I becomes greater than, it will come out and this statement is not executed. For loop condition, it is n plus 1 times. For this, it is n time. Will all of you agree with me? Yes or no?
Yes, sir.
Yes, sir.
Now take a paper and pen. Now our amount of time the algorithm to multiply m and n by repeated addition is going to take is approximately equal to unit time for assignment. How many times we are doing? 1 time, 1 into 1. Then 3 operations are done for n plus 1 time. It is 3 into n plus 1 time. Then when we add and assign p plus m and the added value is assigned again overwritten on p, this particular statement, each statement will take 2 units. Number of times which we are doing is n times, so it is 2n. So the time is proportional to the 1 plus 3 into n plus 1 plus 2, 1, which becomes equal to 5n plus 4. T is approximately equal to 5n plus 4. If n is 2, number of elements to sort, if the numbers are n, if you are making it for n time in the sense, if I say 12 should be added 2 times, how much time it's going to take? How much units of time you are going to take? If n is 2,
14.
14. If n is 3,
19.
for our example, it was m is 12, n is 6. So how much it's going to take? 34. Yes or no?
Yes, sir.
As the input size increases, the amount of time it's going to take increase. It's a linear function, isn't it? It's a linear function. Your amount of time taken for increase in the input size is linear, right? The change is linear. So this is a linear equation. All right. Now, if 12 has to be multiplied by 100 times, so n is 100, 504, 1000, 5004, 10,000. So if n is very large, then your 4 become insignificant. Yes or no?
Yes, sir.
Correct. So we can always say t is approximately equal to 5n. Yes or no?
Yes, sir.
Where is this 4 coming from? See here, 1, n plus 1 in 1, 3 and 1 statement assignment, right? This 1 plus the for loop which is executed for n plus 1 time. That is the constant 4 in your linear equation. And this remains same. Even if your input size n increases to 1 lakh, then 1 lakh into 5 plus 4. So the constant which here becomes insignificant, that is, this is lower order term, right? So the lower order term become insignificant and we will be concentrating on the higher order terms. So t is approximately equal to 5n. We can say t is approximately equal to 5n. We will say for the large value of n, t is proportional to n and the amount of time it is taken is in the order of n, we are going to say. So in detail, we will see why this is order of n, and this constant also will not come into picture later. But as of now, you know that t is proportional to 5n. Is that clear? Now you can tell me the statement I have made here. We said notion of unit time consumption for each operation. Then we said count the number of times each of the algorithm instructions are executed. Did we do that? Did we count the number of times each of the algorithm instructions are executed in our algorithm for multiplying two numbers? Did we do that or not? I'm asking you all. Hello, are you there?
Yes, sir.
Each operations we have taken care in our algorithm?
Yes, sir.
Do you say it is difficult and it's also unnecessary?
Yes,
Now
sir.
you agree with me?
Yes, sir.
So it's unnecessary because you saw that the assignment and one-time comparison to come out of the loop is 4 units, becomes insignificant, n becomes larger. So what is that we should concentrate on if you're looking at algorithm? In our framework, what should be, when we are trying to measure the time, on what things we should concentrate on?
So the input size?
Input size.
Input size? Are you looking at only input size in this equation?
Number of times, frequency.
Number of times. Number of times of every statement in our algorithm?
Looping statement.
Yes, very good. So where we are going to get this n or n times is the, our framework should concentrate on. Thus the established framework for analysis of algorithm for time efficiency, what we suggest here is measure the most basic operations, the number of times the most basic operation is running in your algorithm. We need to count the number of times each of the algorithm operations is executed for getting this equation, or we said this is unnecessary. So we need to only count the basic operation. The basic operation in our algorithm is the operation which is contributing the most to the total running time, and compute the number of times the basic operation is executed. So what is important, which is contributing to most of the total running time is the most basic operation. In sorting, what is the most basic operation if you are writing a sorting algorithm? Can anyone tell me? You need to find the most basic operation in our algorithm. That will suffice. You don't have to execute every check the time taken for every statement. So what is the most basic operation done in sorting inside the loop? When you sort, what is the most basic operation?
Comparison. Is it comparison, sir?
Comparison, isn't it? Ankit, is it comparison?
Yes, sir.
When you search an element in an array, what is the most basic operation which you are going to do in your algorithm?
You're going to search each and every element for the
Again, what is the operation which is
particular
most
element.
basic here?
You're comparing like that
Comparison.
particular key with that all the elements of an array.
Right, correct. So it's not difficult to find most basic operation in given any algorithm, isn't it? So we will be concentrating on most basic operation, and we'll see what is that most basic operation is all about, right? Okay, so we will be, by this we have concluded that we don't have to check every statement, the time taken by every statement in an algorithm. We should be concentrating on most basic operation. That is the second point in our analysis framework, right? Measuring an input size is the first one. For measuring running time, we are going to find the most basic operation. That is the second step in our formal framework, which we are going to come up for analysis of algorithm. Okay, so let us check. So the total computing time is bound by t approximately 5n plus 4. In this case, it's a polynomial function which we got, which is in particular, it's a linear function here, as I told you. This function obtained by strict sense analysis give the actual computing time function, right? So almost actual computing time, because we have included all the statements, even assignment, storing 0 in P also we have included. That means to say T is equal to some constant time. So constant time depend on the machine. For each instruction, how much time it's going to take, that's C into 5n plus 4, right? So each operation is executed. For executing each operation, some time your machine going to take. If that constant is C, then your T is equal to 5n plus 4. So T is in the order of n. So T always will be lesser than equal to some constant time of n. For example, you take m is equal to 12, n is equal to 2, then you check for 4, then you check your time also increases linearly. So this is a linear equation. That is the graph which is shown here. So this is the second point in framework. First one is to find the measuring an input size, because it takes longer to sort larger array, multiply larger matrices. So we need to measure the input size in an algorithm. Then while measuring, should we use some unit like second, milliseconds? If you are going to do that, it depends on lot of other factors, external factors, which we wanted to avoid, because we are interested in only algorithms efficiency. So we came up with an idea of unit time notion. Once we came up with an unit time notions and we said every instructions in our algorithm, we will see how much time it is going to take. It is very tedious. If there are 1,000 lines of code, every statement you try to see and see how much time it is going to take. It is a tedious process, and later we have also proved that it is unnecessary. So that's the thing which we have discussed as of now, the 2 steps in coming up with algorithm framework, right? So the next one is, as I said, that we count the number of times algorithm basic operation is executed. What is basic operation for us? The most important operation of the algorithm, the operation contributing the most of the total running time. For example, the basic operation is usually the most time consuming operation in the algorithm's innermost loop. So innermost loop, the most basic operations will be available and you need to find out those operations. So for example, basic operations examples, search for a key in a list of n items. Input size is number of items in the list n. The basic operation is key comparison. All of you agree? To add two matrices of dimensions of matrix, if it is given n, then the size of the input size which we are going to consider is n. Then the most basic operations which you do in adding two matrices is addition. So the most innermost loop where you have written a loop for addition becomes the basic operation, and count of that operations you are going to consider for our time complexity analysis. If you multiply two matrices of dimension of n, then the operations which you do in the innermost loop is addition and multiplication, isn't it? But compared to addition, multiplication is going to take larger time in our processor. So we say that most basic operation is multiplication, right? So it's not difficult for us to find the basic operations in an algorithm, and also it's not difficult for us to see the instance size or input size. So these are the first two steps in our framework which you are going to do given any algorithm in this course, whether it is in Unit 1, Unit 2, Unit 3, Unit 4 and Unit 5, you are going to check on your input size. And in this couple of lectures, after a couple of lectures, like today and tomorrow, day after tomorrow, we will discuss some examples which is recursive and non-recursive algorithm, for which we are going to find the time taken by an algorithm. So that will be the discussion. Before going to that, there are two more things which we have to discuss. We will be concentrating on orders of growth, and we will see what is this order of growth in the next class. And also we will see the efficiency, the time efficiency or time complexity does not only depend on the number of elements in an input instance, it also depends on the specifics of particular input. So algorithm, the efficiency which depends on the specific of the input and what kind of analysis which we are going to do in that scenario. We are going to do analysis like best case, worst case and average case analysis. In the next class, we will take an example and I'll show you the analysis of best case, worst case and average case for linear search program, linear search algorithm in tomorrow's class. Okay, so that's for today. Thank you. Any doubts, clarifications?